What will soon follow is the 3-day disaster known as the Robinson Annulation. As you'll see, this was less than perfect. In fact, this was downright horrible to do. So, thank your lucky stars that it was me, not you, that had to do this. Originally, what we were supposed to have done, we were supposed to have used our product from the last reaction, the aldol condensation reaction, and then continued on to the a Michael reaction with an aldol condensation again to reform a cyclic product, which would be our Robinson annulation. However, one, I had disposed of my product, not really reading ahead and not really thinking. I quickly resynthesized it, only to find out that I had not nearly enough product to continue. So after uh, sourcing out some help, we eventually switched the reactant to trans-cinnamaldehyde, as you'll see. And that's where we're going to pick up our reaction. Welcome. Starting the next lab here, and I got to start by cleaning the glassware. So that's what we're doing right now. So the original trans-cinnamaldehyde looks something like this. Now, mind you, the pyranol would have had a different functional group on here, but changing it slightly. But right now, this is the structure of trans-cinnamaldehyde. So we're still going to have that vinyl and carbonyl group there that we're going to use. And so we're going to use that instead. And so look for that when we do our measurements. Okay, so at this point, I'm going to try to add my trans-cinnamaldehyde to my flask. I don't need to add much, but I should be able to add enough. It's not fully a chow cone, but it's close enough that we should be able to see the reaction. Let's see. Okay. So, I'm not sure if you can read that, but that reads the mass of trans-cinnamaldehyde is 0.165. Oh, jumping around a little bit. 165. Now this is, I was shooting for 0.152 to get it on similar quantities to my trans chow cone, similar molar quantities. Now that this is zeroed out again, I'm going to try to add my 0.15 grams of ethyl acetoacetate. So I've added a little bit too much, but that's fine. It's now 0.180 grams ethyl acetoacetate. Now I'm going to add about 5 mils of absolute ethanol into there. And swirl until it appears to be fully dissolved. And since they're all liquids, it shouldn't take too much. At this point, I had added 2.2 molar base and a boiling stone to the solution, and I was ready to start. I'd have a video, but unfortunately the camera was shifted and it was all off camera time. Oh well. Now I'm setting up my distillation, well, my reflux apparatus. I got a sand bath fully heated up. Come on. I gotta make sure this is tightened so that this is fully connected. Turn on water, cold water. Got a water jacket running. Our sand bath below this. Now I just let this heat with a gentle boiling for, I believe, about an hour. So you're going to heat in there. Once it begins gently boiling, for about an hour. This is after maybe only 16 minutes or so. It's already dark, much darker. You can see like it's kind of fluxing up the sides and down, but still gonna give it at least an hour. Up until now, as rough as this has been, there was still no horrible errors. However, not long after that video was taken, I went home for dinner and came back an hour or so later to find that the reflux condenser had, the condensing shaft had popped off and water was spilling all over the table. Thankfully, we did not flood the lab. We didn't flood the table. However, it did cause the hot water bath to sand bath to stop heating, and so I had to restart that. I let that heat for at least maybe another half an hour, but still I'm not sure whether that heated for the full hour or not. I know it heated for like 45 minutes, but we'll see. There's not a really good way to tell how long that heated for. So now I'm letting this cool down to room temperature before I add in the water. I think I heated this for long enough. We will see. We will see. There's been some goofs here and there, so I don't know. If this doesn't work, well, we'll be doing it again. Fun. Okay, so I'm now going to add 2 mils of water and put it in an ice bath. And scratch this and try to precipitate this. Gotta find some way to hold this without dropping it. So this solution this solution has to cool for at least 30 minutes. And we're going to scratch it every so often so that it precipitates. And it's supposedly supposed to precipitate slowly. Now, as I said, because we're using trans-cinnamaldehyde, maybe it'll be a little bit faster, but we're going to go with it just in case. We get as high a yield as possible, and then we're going to filter this out and let it air dry overnight. Okay, it's been approximately 30 minutes, so I'm going to take this and try to filter it through a Hirsch funnel, and then wash it with ice water. Let's see how well this works. Big chunk of salt in there. I need to find a way to remove. Continuing the filtration. Some way to get that off there. That filter for, wow. This is my solid, or what's remaining of it after I've let it drain overnight. So we'll see how much I can extract. I'm going to let this dry for a little bit longer. Here goes nothing. So after like nearly 2 days of letting this dry, I'm going to try to extract the solid. Oh, jeez. Oh my god. Okay, that's not. Extract this solid. It's very sticky. I'm gonna go ahead and extract even the whey paper, the filter paper, into this tube to remove the catalyst. I know they're far from ideal, but it is what it is, and it is after drying for 2 days. After I have this as much into this test tube as I can, I'm going to add some acetone. So I'm going to do that in the next few minutes. So in order to try to get more of this off, I'm going to go ahead and add my 0.5 mils of acetone on here, trying to dissolve a lot of this off of here. Well, what I got is what I got. So this is 1.5 mils of acetone. So I'm going to mix this up. I'm going to extract the liquid into a tube to centrifuge. Try to extract just the liquid, or as much as just the liquid as I can. Okay. While I probably don't have any solid in here, I'm going to go ahead and centrifuge this just to make sure. Make sure you always balance your centrifuge. So I'm going to set this for 2 to 3 minutes. I don't need it too long, but you need to centrifuge. Yep. So we're going to come back in 2 to 3 minutes. In the meantime, I'm going to weigh out a new test tube for my sample. So I'm clean. I'm trying to get the weight of test tube. I'm going to put in 16.258. Now I'm extracting my tube from the here. Get my tube. Maybe there's no solid in here, but we'll go ahead and just making 100% sure. Now we're going to evaporate this to dryness and get the weight. So now it's just the process of heating this until dryness. Now we won't be able to get a melting point because I can't seem to find a typical structure online. We can get a melting point, but we won't be able to tell how accurate it is. But we will be able to tell IR, and IR should be pretty definitive whether we have reaction or not, as we're going to see a loss of aldehydic peak as it's converted into our one structure. Attempting to dry this, it just become a paste, kind of oily paste. I don't think I can get crystallization, so my sample weight is 16.344. May have lost a little bit trying to crystallize it, the spatula, but do it. 345. At this point, I ran an IR of both starting materials, which is trans-cinnamaldehyde, ethyl acetoacetate, and my product. And this way we can compare the three. Please note in this spectra, the red spectra is my product, while the other two are my reagents. Okay, let's see how well this looks. So the top spectra here is our product. The bottom two, the middle one is ethyl acetoacetate, and the bottom one is trans-cinnamaldehyde. Let's look at these each individually. So the bottom one, you notice there's a peak at 3021. That is from our phenyl. Well, it's most likely from our phenyl group and from our cinnamaldehyde. And we have the alkene stretches, the sp2 hybridized peaks. We have the peak at 2810 and 2745. The 2745 you should definitely take note of, as that is most likely our aldehydic CH. Over here we have stretches at 1664 and 1624 and 1573. The 1664 most likely are conjugated aldehyde. 1624 most likely are alkene, and the 1573 is most likely our phenyl. The phenols typically don't come nearly as far upfield as the others. Now, as we look at the ethyl acetoacetate, we have a peak 2887, only CH sp3 hybridized stretches, and we see two distinct C double bond O peaks at 1711 and 1734. Now here with our run, we still see the 3028 peak, which would be our part of the phenyl group in our alkene. We see a new 2930 peak, which would be the sp3 hybridized carbons we have just added, both through the ethyl acetoacetate and part of the reaction that suddenly makes some CHs sp3 hybridized instead of sp2. We still see some of the carbonyl stretches of 1672 and 1712. They've changed a bit, but remember there's still a carbonyl in there, and especially at ester peak. And we still see the phenyl peaks at the 1606, and we see some other alkene messes in 1672 and 1650. In addition, we should expect at least a pretty sharp, a pretty strong CO peak as part of the ester between the 1300 and 1000 region. And I think those 1362 or 1217 are probably associated with that. As you can see in this one, I overlaid the three spectra so you can see where there are similarities and differences in it. You can see the blue spectra, how they almost perfectly overlap in the sp2 hybridized region. How the ethyl acetoacetate, the CH3 sp3 hybridized peaks are not in the same positions. They are new and unique. And those aldehydic CHs are definitely different from what we have. So down here we see a lot of overlap from the ethyl acetoacetate, the green and the red, and the first C double bond O region. And we see some of the overlap from our trans-cinnamaldehyde with the light blue, suggesting that we have a mixture of the two, but it's not just one or the other. Because there's a lot of peaks we should expect to see that we don't see. So it's not just we have both reagents mixed together. After running the IR of the crude product, this is where I choose to stop. Since the product is more of an oil than a solid that I can't really get crystallized. I'm not going to bother to try to recrystallize it. It's not crystalline to begin with. And because it's not crystalline, there's not really a purpose of doing a melting point. I don't think I could achieve that noticeably. Even if I did, I'm not sure what the melting point should be, so we are not going to bother to do that. But so that will be the lab right here.